Let's start with something simple. You're standing in front of a mirror, right? And you see yourself. Light goes from you to the mirror and bounces back to your eye. Now, if I ask you, which path does the light take? You'd probably say, well, it goes straight to the mirror and bounces back. And you'd be right, but that's not the interesting question. The interesting question is, why does it take that particular path? You see, back in ancient times, a fellow named Hero of Alexandria noticed something remarkable. He said that when light bounces off a mirror, the angle it comes in at is equal to the angle it goes out. The angle of incidence equals the angle of reflection. That's a rule. But why? Why should light obey this rule? Now, Hero had an idea. He said, maybe light is lazy, maybe it takes the shortest path. And you know what? He was right. If you have a point here and a point there, and you want to bounce off a mirror in between, the shortest path is exactly the one where the angles are equal. You can prove it with geometry. It's beautiful. But then things got more complicated. What happens when light goes from air into water? You've seen this. Stick a pencil in a glass of water, and it looks bent. The light changes direction at the surface. We call that refraction. And there's a rule for this, too, discovered by a fellow named Snell. He said that the sine of the angle in air divided by the sine of the angle in water is always the same number. Always. For any angle you try. That number tells you something about the water. We call it the index of refraction. Now, here's where it gets interesting. In the 1600s, there was this French lawyer, Pierre de Fermat, who liked to think about mathematics and physics in his spare time. And Fermat said, wait a minute. Hero said light takes the shortest distance. But when light goes into water, it doesn't take the shortest distance. It bends. So what's going on? And then Fermat had a brilliant idea. He said, maybe light doesn't care about distance. Maybe light cares about time. Maybe light takes the path that takes the least time. Now, this is tricky, so let me explain it with a story. Imagine you're a lifeguard on a beach and you see a beautiful girl drowning in the water. She's out there screaming for help. What do? Well, you want to get to her as fast as possible, right? Now, you can run faster than you can swim. So if you just run straight toward her and then dive in, you're going to spend a lot of time swimming slowly. That's not good. On the other hand, if you run all the way down the beach to the point that's closest to her and then dive in, well, that's a long way to run, isn't it? The best thing to do is something in between. You run at an angle, you dive in, and you swim at an angle. And if you work it out, if you calculate which path gets you there fastest, you find that the angle you should run at and the angle you should swim at are related by exactly the same rule as Snell's law for light. The faster you go in each medium, the more you want to stay in that medium. Light does the same thing. It goes slower in water than in air, so it bends its path to spend more time in the air where it's faster. So Fermat said light always takes the path of least time, not shortest distance, least time. And this works. It explains reflection, it explains refraction, it explains everything. Hero's shortest distance is just a special case when the speed is the same everywhere. But now, and this is where it gets really peculiar, now we have to ask ourselves, how does the light know? I mean, think about it. The light leaves here, and somehow it has to figure out, if I go this way, it'll take me 2.3 seconds. If I go that way, it'll take me 2.7 seconds. This way over here only takes 2.1 seconds, so that's the way I'll go. How does it know? Does it send out little scouts to check all the paths? Does it have a brain? This bothered Fermat. It bothered everybody. It makes it sound like light has a purpose, like it's trying to do something. It's not a causal explanation where you push something and something else happens. It's a teleological explanation where the end determines the means. And that's philosophically very strange. How can light know in advance which path will take the least time? Well, I'm going to tell you something absolutely wonderful. The light does know. And the way it knows is even more amazing than you might think. The light doesn't just check the path of least time. The light checks every path, every single possible path from here to there. And I mean every path. The straight path, the curved paths, the crazy zigzag paths, the paths that go around the moon and back, every path. Now, you're probably thinking I've lost my mind. But wait, let me explain how this works. In quantum mechanics, and this is the strange theory of light and matter, every path has what we call an amplitude. You can think of it like an arrow, a little spinning arrow, that represents the contribution of that path. For each path, the arrow points in some direction. And to find out the total amplitude for light going from one place to another, you add up all these arrows from all possible paths. Now here's the beautiful part. For most paths, the arrows point in all different directions, and they cancel each other out. If one path gives you an arrow pointing this way, another path gives you an arrow pointing that way, and they cancel. But, and this is crucial, for paths that are close to the path of least time, the arrows all point in nearly the same direction. They add up, they reinforce each other. So what actually happens is this: all paths contribute, but only the paths near the minimum time path contribute constructively. The other paths cancel out. And that's why it looks like light chooses the path of least time. It's not that light is smart, it's that nature is quantum mechanical. And in quantum mechanics, everything explores all possibilities. Let me give you a concrete example. Suppose light is reflecting off a mirror. We can divide the mirror into little sections, and we can ask, what's the arrow for light bouncing off this section? What's the arrow for light bouncing off that section? If you draw these arrows out, and I've done this with students, you see something remarkable. Near the center of the mirror, where the path takes the least time, all the arrows point in roughly the same direction. They add up constructively. But as you go toward the edges of the mirror, the arrows start spinning around faster and faster, and they cancel out. So most of the light comes from the center of the mirror, where you'd expect it classically. But here's what's really strange. If you cover up that center part and leave only the edges, you still get some light. Not much, because most of those edge contributions cancel, but you get interference patterns, you get diffraction. The light really is using all parts of the mirror. And this isn't just theory. You can test this. If you take a mirror and etch grooves in it, little grooves spaced just right, you can make the arrows from different parts of the mirror point in the same direction, even for parts that aren't at the minimum time. And then those parts contribute too. That's how diffraction gratings work. We're forcing all the paths to cooperate, to add up constructively. Now let me tell you about refraction. Light going into water. Same principle. Light takes every possible path from the source to your eye. Some paths go straight down through the surface, some paths go at an angle, some paths zigzag around. Each path has its arrow. But again, only the paths near the path of least time, which happens to be the path that obeys Snell's law, have arrows that add up. The other paths cancel out. So Snell's law emerges from this deeper principle. Light explores all paths, but only certain paths matter. And here's something that will really bake your noodle. The light going through the water is actually affected by the glass, not just the glass in its path. All the glass, all the atoms in the water, or glass that the light could have interacted with. You see, when light goes through a material, it's interacting with all the atoms. Each atom scatters the light a little bit, and all these scatterings add up. The light slows down in the material, not because something is blocking it, but because of all these interactions with the atoms, which add little delays. And if you work this out in detail, which I did in my lectures at Caltech, you find that the index of refraction, the amount by which light slows down, is related to how the atoms respond to the electromagnetic field. The light makes the electrons in the atoms oscillate, and these oscillating electrons emit their own light, which interferes with the original light, and the result is that the combined wave travels more slowly than light in vacuum. It's all interference. It's all this quantum mechanical adding up of amplitudes. Now, I want to emphasize something very important. When I say light takes every path, I don't mean that there's a little photon that splits up and goes along every path. That's not it at all. What I mean is that to calculate the probability amplitude for light to go from A to B, you have to include contributions from every possible path. It's a calculation rule, but it's a calculation rule that reflects something very deep about how nature works. In the quantum mechanical world, particles don't have definite paths. An electron doesn't go from here to there along one path. It has an amplitude to go along every path. And the same is true for photons, for light. The idea of a particle following one definite path is a classical approximation, something that works well for big things like baseballs and planets, but breaks down for small things like electrons and photons. And this is not just philosophy. This is something we can test. You've probably heard of the double slit experiment. You shoot light at a barrier with two slits in it, and you get an interference pattern on the other side. How can light going through one slit interfere with light going through the other slit? It's because every photon has an amplitude to go through the left slit and an amplitude to go through the right slit, and these amplitudes interfere. The photon is, in some sense, exploring both paths. And if you try to be clever and figure out which slit the photon went through, if you put a detector there to check, the interference pattern disappears. Why? Because now you've changed the experiment. You've made a measurement. And when you measure which path the photon took, you're no longer adding up amplitudes from different paths. You've collapsed the system into one path or the other. The quantum interference is destroyed. This is what makes quantum mechanics so strange and so beautiful. The very act of measuring changes what happens. Nature isn't just sitting there already decided. The possibilities are all there, all the paths, all the alternatives, and they all contribute. It's only when you make a measurement that you get a definite result. Now you might ask, but Feynman, this is crazy. Are you telling me that when light goes from Los Angeles to New York, it's also going via Jupiter or via Alpha Centauri? And the answer is yes, in principle. But the amplitude for those crazy paths is so small, and they cancel out so completely with other crazy paths that they don't matter. For practical purposes, for light going long distances through empty space, only the paths close to a straight line contribute significantly. But for light traveling short distances or light interacting with matter, these other paths can matter. That's why you get effects like diffraction, where light bends around corners. That's why you get effects like tunneling, where a particle can get through a barrier that it doesn't have enough energy to climb over classically. All these quantum effects come from the fact that particles explore all possible paths. And this principle, this idea of adding up amplitudes over all paths, is not just some mathematical trick. It's at the heart of quantum electrodynamics, which is our best theory of how light and matter interact. With this theory, we can calculate things like the magnetic moment of the electron to 10 decimal places. It's the most accurate theory in all of physics. And it's based on this idea, that every possible process contributes with some amplitude, and you add them all up. So when you ask, how does light know where to go? The answer is, it doesn't know, not in the sense you mean. There's no little intelligence inside the photon making decisions. Instead, nature works by a different principle. All possibilities exist as quantum amplitudes, and these amplitudes interfere. The paths that matter, the paths that don't cancel out, are the paths near the classical path of least time. But all paths contribute, and that's what makes the quantum world so strange and wonderful. And here's the kicker. This isn't just true for light, it's true for everything. Electrons do it, protons do it, even big molecules do it, as long as you're careful not to disturb them. Everything in quantum mechanics explores all possible paths. You're only seeing the classical world, the world where things follow definite paths, because the quantum interference becomes so perfect for big objects that only one path, the classical path, survives. You and I were made of quantum particles. In principle, there's an amplitude for you to suddenly appear on the moon, but that amplitude is so incredibly tiny, and it's canceled so completely by amplitudes for other paths that it never happens. The quantum world is there, underneath everything. But for big objects like us, it averages out to classical behavior. But for light, for electrons, for the small things, the quantum weirdness is right there on the surface. And that's why light knows where to go. It doesn't know, it explores, it tries everything. And nature, through the magic of quantum interference, makes only certain paths matter. Isn't that wonderful? To me, this is one of the most beautiful things in all of physics. We started with a simple question about reflection and refraction, and we ended up discovering that nature works in a completely different way than our everyday intuition suggests. The world is quantum mechanical at its core, and light is showing us that every single time it bounces off a mirror or bends through water. So the next time you look in a mirror or see a rainbow or watch light streaming through a window, remember, that light got to you by exploring every possible path. Most paths canceled out, but all contributed. And that's how light knows where to go, by trying everything everywhere all at once. Nature is more clever than we ever imagined, and more beautiful too.